we learned about the binomial distribution. We learned that it was a counting variable that counted the number of successes in a fixed number of trials. And we looked at 4 specific criteria to check to ensure our counting variable is in fact a binomial random variable. Now we're going to add on to that. If we verified that a variable is binomial, so this only works for binomial, what I'm about to write down, nothing else. If it is in fact binomial, then we have some shortcut formulas for the mean and the standard deviation. So we said that the binomial variable was a specific type of discrete. And if you remember in the last section, we had the mean of a discrete variable. We used mu to talk about theoretically what we would see was adding up all the possible values. In our binomial setting, that would be anywhere from 0 successes up to n successes, and multiplying it by the probability of each. Now, when you plug in the specific formula for probabilities here when something follows a binomial distribution, then this formula simplifies very nicely. Again, only for binomial. Don't try and use it anywhere else. So the mean for binomial simplifies nicely to n times p, number of trials times probability of success. And we'll see how that's fairly intuitive in just a moment. The standard deviation, if you remember for data, we typically use S for data. We're talking about theoretically now for the whole population, so we're going to switch over to Greek letters. So I don't think we've seen this one before, so lowercase sigma. So lowercase sigma to represent the standard deviation for the whole population. And that's going to be square root of n times p times 1 minus p. So all of this is under the square root. So let's do an example and see how that makes sense and has a little bit of intuition in a setting. So here it says in the NBA, top free throw shooters usually have a probability of about 0.9 of making any given free throw. And I'll just say that some people argue that their shots are independent because they have so much muscle memory and training built in that they are pretty much independent of one another. So we're going to assume that's the case. So we've got our binary outcomes of success and failure. We've got our independent trials. We're going to go with it since these are top-level players and have that muscle memory built in. Number of trials fixed, they're going to shoot 10 free throws. 90% chance of making those, and X, our counting variable, is going to be the number of free throws they make out of those 10. So here it wants us to state our distribution and use that shorthand notation. So in our mind, we've kind of checked off those 4 criteria. So we can say X, remember this little tilde, you could just read it as can be modeled by. So X can be modeled by this binomial distribution meets the 4 criteria. The first number I'm going to put in, right, should be 10, the number of trials, and the second number should be 0.9, the probability of success. So there's my short way to sum up mathematically this experiment or this setting, this random variable counting up number of free throws. Now I want to find the mean and the standard deviation of this particular random variable. So first, let's try the mean. We're going to use that symbol of mu. And just think about this in plain English for a moment. If I'm going to take 10 shots, I make 90% of the shots. How many would I expect to make? Sure, 9 out of 10. And that's exactly what the mean does. Our formula was n times p, so 10 times 0.9, or in other words, finding 90% of 10. And that would give us 9 shots. The next part is finding the standard deviation. And that formula, not quite as intuitive, n times p times 1 minus p. So plugging that in, our n is 10, our p is 0.9, 1 minus p is 1 minus 0.9 or 0.1. And if you work that out, don't forget the square root. Double check this, 0.9487 shots. So this is telling me if a player takes 10 shots, on average, he's going to make about 9 of those. I expect that to vary by around 1 plus or minus 1-ish each time. Notice I didn't round this, leave it as a decimal. Let's get a start on the next example. In this one, we're looking at a research poll done in 2010 that's looking at tattoos and how they kind of evolve and change with culture across generations. So they found out that Pew Research poll found that 38% of millennials have a tattoo. And we're going to define X, this counting variable, as the number of young adults with a tattoo in a random sample of 20. Okay, so first thing we want to do is state our for condition for this to be a binomial random variable. I'll let you maybe pause and try that on your own. Okay, hopefully you've written down bins or for criteria, but don't stop there. Binary outcomes was what the B stood for. Write that down. I stood for independent trials. N was that we had our number of trials fixed before we even start this experiment. And S was the fact that we had the same probability of success for each of our trials. So let's double check each of these. Our binary outcomes, we're checking if each subject has a tattoo. That's our success, or what we're counting here, or no tattoo. That's going to be our failure in this case. Okay, independent trials. Now be careful on your wording here. There's something in the problem setup that ensures us that these are independent trials. And hopefully you picked up on that wording here. We have a random sample. That guarantees we have independent trials. We don't have a bunch of friends we're asking, a bunch of people that are in the military together we're asking. It's a random sample of millennials. So that ensures us that our trials are independent. Okay. Number of trials fixed, they tell us pretty clearly their number of trials or millennials they're going to ask are 20. And then the same probability of success, our P they give us is 0.38. So our four criteria we can verify. So we'll sum that up with our shorthand notation. X is binomial. First value we should put in there is our 20, the number of trials. And second value, our 0.38, the probability of success. Next, let's practice finding the mean and standard deviation for this variable. So mean is mu. Standard deviation, we've got our new notation, this lowercase Greek sigma. And again, the formula should make sense. Mean is n times p. So all we're doing is finding what is 38% of 20. We have 38% successes, so figure out what 38% of 20 is, and you're going to get 7.6 people. And again, that's weird to say 7.6 people. No worries, just leave it as a decimal. We're talking about average behavior. And then here, we've got our n times p times 1 minus p, all under the square root. So our n in this case was 20 times 0.38 times 1 minus 0.38. Make sure you can do all this on your calculator, okay? So pause and try it if you need to, and you're going to get 2.17 people. So this is saying if I did this experiment over and over again and recorded how many out of 20, the average of all those numbers would be around 7.6, plus or minus a couple of people. All right, in the next videos we're going to be learning how to use our calculator to find probabilities for the binomial distribution. So go ahead and get that handy.